and Fermi level.
Yes.
Okay, so I will first read the note that I provided you, and then I will explain this figure. Hall effect. So you have done this practical in your first semester, in your MSc first semester, Hall effect. So you found out, I think, Hall resistance, then Hall coefficient, and mobility. And what else did you find out? Oh, what type of semiconductor is it, right? It is N-type or P-type semiconductor, right? So, okay, so I'm reading the note and then I will explain the figure. So, Hall effect in 1879, E.H. Hall, E.H. means Edwin Hall, he a British scientist. He observed that when an electrical current passes through a sample placed in a magnetic field, okay? So you have a sample, you have a conducting sample, and you pass electrical current through that sample. But again, what is another condition? Another condition that the sample is placed in a magnetic field. Okay, then what happens? What he observed that a potential proportional to the current and to the magnetic field is developed across the material. Okay, so a potential difference was found to be developed uh, across the material, which was numerically found proportional to the current and the magnetic field. Okay, and there is another condition. The condition is that the potential which was developed across the material that was found to be perpendicular to both the current and the magnetic field. Okay, this effect is known as Hall effect, and this is the basis of many practical applications and devices such as magnetic field measurement and position and motion detectors. Okay. Then next we wrote about some applications of Hall effect. So some applications of Hall effect are determination of semiconductor type, whether a semiconductor is a P-type semiconductor or it's N-type semiconductor. So that can be determined from carrier density. Carrier means what is the density of in semiconductor. Okay, so this can also be measured from Hall measurements. The mobility is then measurement of magnetic field. This is also can be done from Hall effect measurements, and measurement of power in an electromagnetic wave. Okay, so this was not done, of course, in your practical, but these are some of the applications of Hall effect. Okay. Now, I hope all of you can see this particular figure, and I will try to explain this a little bit. So here we have a sample, okay, a conducting sample. This particular color, I don't know what color this is called, but anyway. And this semiconductor sample, and here it is written that it is N-type semiconductor. N-type semiconductor means electrons are the majority carriers, okay, N-type. So what is going on here? So you can see that current is flowing through this material. The current enters from the other side, and it is the direction of conventional electric current, I. Okay, the I is the current flowing through the material. And there is another condition. What is the condition? That this particular semiconductor material or whatever metallic material is there, that must be subjected to a magnetic field. Okay, the magnetic field is B. That you can see the magnetic field is pointing upwards. Okay, so we have the current I, written in black, and magnetic field given in blue, the arrow upward, arrow pointing upward. Okay, so these are the two preliminary conditions. And you see one thing, the current and the magnetic field are perpendicular to each other. Okay, the current is flowing along the sample, but the magnetic field is in a direction perpendicular to the sample. Okay. Now, what Hall observed? Hall observed if this happens, then what happens? A potential difference is developed across the material. So which one is the potential difference here? VH. VH, you see, it's given here VH. So a potential difference is developed across the material, which is perpendicular to both the current and the magnetic field. So VH, you can see, this is the potential difference, and this is developed from one end of the material to the other end. Okay. And you can see this particular voltage, VH means Hall voltage. Okay, H in the subscript means it stands for Hall voltage. Okay, so this Hall voltage is perpendicular to both the current and the magnetic field. In other words, what is going on? So the current, the magnetic field, and the Hall voltage all are perpendicular to each other. Like the current is perpendicular to the Hall voltage, the current is perpendicular to the magnetic field, and the magnetic field is also perpendicular to the Hall voltage. So you understood this figure, how they are perpendicular? Like, okay, if you draw the current, maybe current is directed like this. Okay, I'm just drawing with the help of a very simple figure. Then you have a magnetic field. Okay, magnetic field is pointing upward. Then there is a voltage, something like this, which is perpendicular, which is developed across the material and perpendicular to both current and magnetic field. So again, you know from electricity, basic electricity, that when is a voltage developed across a material? When you have to, potential difference means when you have to carry a charge from one place to another. Okay, or you have to do some work in order to move a charge from one to another place. So what happens here? So you see on the left side of the material, negative charges or electrons have gathered, and on the right side of the material, positive charges have gathered. Okay, so there is a charge difference on the on either side of this material. Okay, so positive charges are on one side, and negative charges are on another side. And this charge difference across the specimen is the main reason why Hall voltage is developed across the material. Okay, and why this happens? Because Fe you can see in the red in the picture, it is the electric force from charge buildup, and Fm is the magnetic force. Okay, magnetic force, this is the nothing but the Lorentz force. Lorentz force, I think you have read in your 10+2 level also, and BSc level also. So there is an electric field associated with the material, because why? Because there is an electric current. Okay, and also there is a magnetic field. The sample is subjected to a magnetic field, which is denoted by this B. And due to both the electric field and magnetic field, there will be a force, Lorentz force. And actually this Lorentz force is responsible for separation of the charge carriers. Electrons move to one side and holes move to the positive carriers move to the other side. And because of this Lorentz force, electric force and magnetic force, what is happening? charges are being separated, and this separation of charges is the actual reason why a voltage, no? So charges are separated, so there will be a potential difference between the two ends of the surface, and this potential difference gives rise to Hall voltage. Okay, so I hope you understood how Hall voltage is generated, more or less. Okay, so I delete this. Okay, so this is the case when the semiconducting material is of N type. Okay, so there is another figure here when the semiconductor material is P type. In P type, what happens? If this is the current, same is the direction of current, and same is the direction of the magnetic field, then again positive charges move to the left side and negative charges move to the right side, and again a Hall voltage is generated, VH. Okay, so this time the charges are the charge buildup is different, because this time the majority carriers are the positive charges in the semiconductor. In the earlier case, in this figure, the majority charges were the electrons, and therefore the electrons move to one side and holes move to another side. And in this case, in the second case, the holes are the majority charges. This is a p-type semiconductor, and therefore holes have moved to one side, and the minority carriers or electrons have moved to the other side. So nevertheless, we will be able to observe a voltage being developed across the material called as Hall voltage, and this Hall voltage is perpendicular to the both current and the magnetic field. Okay. So this is more or less, if you read this, you can, Hall effect is a very popular phenomenon in physics. You have done practical in the last semester also. I think you can understand it from the figure, more or less. So I think in your syllabus, there is a topic given, Hall effect in metals and semiconductors. Okay. So that thing, so Hall effect in metals and semiconductors, so that thing we can discuss in brief, and that note has been given to you. So okay, can you give me 1 minute? I will check your syllabus quickly. Just give me a minute. I'll check your syllabus. Okay, so in your syllabus it is given Hall effect in metals and semiconductors. Nevertheless, we introduced Hall effect briefly, but Hall effect in metal and semiconductor, let us discuss it quickly. So I will just read the note, and if you have the note with you, it will be better, I guess. I hope all of you have written down the notes which are uploaded to Google Classroom. Okay, so I'm reading out the note. So it is written, we imagine that the charge carriers move in a medium that offers some resistance. Okay, so we all know that whenever a current or electric charges move in a medium, they experience resistance. Okay, resistance to the motion of charge carriers. Okay, the resistance is due to scattering between carriers and impurities in the material, and between carriers and vibrations of materials atoms. Okay, so all of you know why electrical resistance is generated in a material. That is because the charge carriers suffer collision with impurities present in the material. And whenever they suffer collision with impurities or atoms of the materials or ion cores, in that case, the charge carriers will experience some resistance. Okay. A resistance means their motion will be hampered, and that motion will give rise to electrical resistance. Each charge carrier is accelerated by applied field, but often it scatters and loses energy. Okay. If we assume that the average time between scattering events is tau, then we have on average a retarding force acting on the charge carriers. Okay. So the charge carriers, they undergo scattering with the impurities present in the material, etc. And if tau is the time of scattering, tau is the time between two scattering events. Between two scattering events means, suppose we have one atom and we have second atom. So with the first atom, the charge carrier will undergo some collision or scattering, and the time in which it will undergo scattering with the second atom, that is called the scatter. What is it called? Average time. That is the average time of collision between impurity atoms or simply materials atoms. Okay. So the time interval between two collisions is the scattering time. Okay, or the average time tau, which was given in your note. Okay, so if tau is the time, and then a retarding force will be there as given in the note. What is the retarding force? Because the charge carrier undergoes some resistance. It feels a resistance. Okay, so the resistance is kind of a negative force. Negative force means okay, force is not negative, but since its direction is opposite to the motion of the charge, its charge is moving from left to right, then due to the collision with an atom, the force will be in the opposite direction. Okay, the charge carrier will experience a force in the opposite direction, and that is the retarding force. So the retarding force is vector symbol, it is given, and it has an expression of m v vector divided by tau, where m is the mass of the charge carrier. Like charge carrier may be electron or hole, depending on the semiconductor is p type or n type. Okay. So since the direction of the force is opposite to the motion of the charge carrier, therefore the retarding force is given with a negative symbol. Okay. Okay. Now what is going on here? So there is one expression given under the influence of applied electric and magnetic fields from Newton's second law. So there are two forces now. One is the Lorentz force and one is the retarding force. Okay. So Lorentz force is the force due to the electric field and the magnetic field. Okay. So when because we know that this particular semiconductor material is subjected to both electric and magnetic field. The electric field because of the current, and magnetic field, it is also applied to the material. Therefore, from Newton's second law, where there is an expression given, equation 2 given in their note, which is m dv vector over dt, which is the mass into acceleration. Well, I mean, we want to find the total force acting on the charge. Okay, what is the total force? Suppose that total force is m dv vector over dt. This is equal to q multiplied by e vector plus v vector cross b vector. So that is the Lorentz force you know already from your previous classes, minus mv vector over tau. So actually it should be plus like this. It should be Lorentz force plus the retarding force. But the retarding force that we just introduced in equation 1, that has a negative symbol, and that is why it has become it is a minus sign. So Lorentz force and the retarding force. Okay, but the retarding force has a negative symbol. Okay, then the next paragraph I will read out. At steady state, the time derivative of v vector will vanish. Under the usual convention that b vector points along the z-axis, we obtain component of vector v by setting the left-hand side of the equation 2 to 0. Okay, under a steady state means here suppose the charge carrier is moving with a uniform or constant velocity. Okay, so as we know, if one body or a particle is moving with a uniform or constant velocity, then its time derivation is 0, or its acceleration is 0. Okay, therefore the left hand side of equation 2 is made equal to 0. That means the quantity m dv vector over dt is equal to 0. Okay, so we will have only the right hand side. I mean, the right hand side of equation 2 will be remaining, or in other words, we can write it as q multiplied by e vector plus v vector cross b vector equal to mv vector over tau. Okay, so now the thing is then in equation 3 we have written a set of equations, right? So actually there is a derivation involved here from one thing. All these quantities like electric field E vector, velocity V vector, then magnetic field B vector, these are all vector quantities, right? And vector quantities means they can be expressed in terms of I, J, and K unit vector components, right? So, and one thing you have to remember that the magnetic field is only along the Z-axis. I mean, since the magnetic field is taken to be perpendicular to the material, it is taken to be along the z-axis. But others like the electric field or the velocity vector, they can be taken along all axes. Okay, just if I tell you, E vector has Ex I cap plus Ey j cap plus Ez k cap. Okay, if we consider that Ex, Ey, Ez are the component values along x, y, and z direction, and I, j, k are unit vector values, you know already. So if you do some rearrangement like this, so I am not. We have not shown in the notes how the rearrangement is done, because that would be again a long thing. So then we get the set of equations 3. And in the set of equations, we find the values of Vx, Vy, and Vz. So Vx, these are only values. Okay, these are not the vectors or directions. So Vx has a value of like q tau divided by m. Okay, just give me a minute. Okay, can you okay, I think we are not discussing this figure, so no problem. Anyway, so Vx has a value of q tau by m Ex plus q tau by m Bz Vy. Then Vy similarly has some values like q tau by m Ey minus q tau by m Bz Vx. and then Vz has a value q tau by m Ez. So from where these values are coming? These values are coming from equation 2, provided you make the left hand side of equation 2 equal to 0. And when the left hand side of the equation 2 is equal to 0, when you consider steady state of the charge carrier. Steady state means it is moving with some constant velocity. Okay. And the Vx, Vy, Vz component values can be found out from vector cross product. Like as I told you, Ex like E vector electric field vector, consider along all three directions. Then V vector, consider along all three directions, like that. Okay. Okay, so I think you can remember this, because if in exam, if it is asked in exam, you have to write a lot of intermediate steps. So better to remember them if you can. Okay. Okay, then there are again some mathematical steps, like from equation 1, we have that Jx is equal to nq Vx. So Jx is, what is Jx? It is current density. Okay. Jx is equal to current density. Current density means current per unit area. Okay. So J is equal to I over A. J is current density, I is the current, and A is the area of cross section of the material. So you just remember this formula. Jx is nq, n is the carrier density, small n, q is the charge, and Vx is the velocity component along x direction. So similarly will be the corresponding values of J along y and z components. Okay. So this way, if you go on calculating, I think then we get a set of equations 4, and I think you should also try to recall these equations. For expressions for Jx is equal to sigma over 1 plus omega c tau square multiplied by Ex plus omega c tau Ey, like this. Okay. So what is sigma here? Because sigma is a new term coming out, which we did not introduce earlier. Sigma is the conductivity. Okay. And it has a numerical value of nq square tau by m. Okay. So that is the value of sigma. Okay, another term is there. Another term is there which is called omega c. Omega c is called something called cyclotron frequency. Okay, so cyclotron frequency omega has a value of qbz over m. Okay. So cyclotron frequency, I mean, like those of you who will be taking condensed matter physics as elective paper in 3rd and 4th semesters, so they will understand well this cyclotron resonance. So what is cyclotron resonance? So that topic is there in your 3rd semester elective paper, condensed matter physics. Okay. Okay, so briefly about something is given here about cyclotron frequency. So it is the angular frequency omega c is known as the cyclotron frequency. So it is the frequency, okay, the definition, you have to remember it. It is the frequency of rotation of a charge in a magnetic field. Okay. So it is the frequency of rotation. If a charge is rotating in a magnetic field, with which frequency it is rotating under the influence of a magnetic field, that is known as the cyclotron frequency. Okay. And it can be taken as a measure of strength of the field. Okay. Okay, so there is another parameter tau. So tau was earlier some scattering time, or time between two scattering events. And it can also be called as something as relaxation time. Okay. Okay, so there is Jx. In the expressions for Jx and Jy, we have a term omega c tau. So omega c tau is used to characterize the experimental situation. Okay, so some low field, weak field limit and strong field limit. There are two such concepts. So the condition for weak field limit is that this tau has to be very, very small. If omega c tau multiplication is much smaller than 1, then the condition is called something called as weak field limit. Or on the other hand, if omega c tau is a quantity which is much very, very greater than 1, so in that case, it is called as strong field limit. So again, these things you will learn in details if you study condensed matter physics as elective subject in third semester. So that means strong field limit means when the magnetic field is very strong. In that case, the value of omega c tau will be much greater than very, very much greater than 1. Okay. So I think more or less that is the briefly Hall effect in metals and semiconductors. Yeah, I think that's all about Hall effect and its influence on metals and semiconductors. So in other words, either be it metal or semiconductor, there will always be some resistance to the electrical flow or to the current flow. And in that case, this equation 2, which combines Lorentz force and this retardation force, that can be considered. And then you can find corresponding values of Vx, Vy, Vz. And if you find the values of Vx, Vy, Vz, you can find corresponding values of the current density. Current densities are nothing but Jx, Jy, Jz. Okay. And some new terms appear if you find the expression for current density, which are like omega c, then sigma. Sigma is conductivity, omega c is cyclotron frequency. Okay.
Hello, sir. Sir, your
Yeah.
slides are not moving, sir.
No, I am not. I have not changed slides. So slides are
Okay.
just. Actually, I am reading from your notes.
Okay.
The note which I gave you. So these things are not there. So someone is trying to join now. Okay. Let me admit. I think that's more or less about Hall effect. Okay. So after Hall effect, any question you have about Hall effect? So see, there are some derivations related to Hall effect, like the Hall coefficient RH. Then you have to find the N, the charge carrier density. Then you have to find the mobility. So there are some expressions, but those how to derive those expressions, those particular things are not given in your syllabus. So for now, I am not discussing them. Okay. So for now, or means for this current semester, those things I am not considering, because actually those are not given in your syllabus. But anyhow, brief introduction to Hall effect is given. Okay. Okay, so then we'll move to Fermi level. Fermi is an important topic. For Fermi level, I have to move back to the presentation slides. Can you see this figure of Fermi level?
Yes, sir. You can
I
see.
hope you can see. Okay, good. Okay, in the meantime, I take some screenshots. Okay, because you take some 1 or 2 minutes break, I will quickly grab some screenshots. Day 1. Day 2. Today date is 27/06/20. Okay, I will grab another screenshot. Okay, so can you give me just 1 more minute break? I'm coming soon. Okay, just you also take some break if you want. I'm coming back soon. Okay, I am back. So what are you doing now? So there is no another round of lockdown. So how many of you live in Guwahati? So huh?
None of us, sir.
No one. So in Guwahati, they are beginning full lockdown from Sunday night,
Yes, sir.
and others if living in town, any town area. So there is like again lockdown Saturday and Sunday.
Saturday and Sunday, yeah.
Yeah. So lockdown. Okay, so let's start with our Fermi level. Okay, so what are Fermi levels? So Fermi levels are nothing but some energy levels related to the band energy of a material. Material may be metals or semiconductors, like that. Okay. And Fermi level mostly talks about the distribution of electrons in different energy levels. Okay, so there are energy levels, we know valence band, conduction band, and so on, so on. So what is a Fermi level and how the electrons are distributed? Okay, so I will read some notes from the notes given to you for your class, and then we'll try to discuss those things. Okay. Okay, so this is the figure of Fermi level. So the caption is there. It was given to you during the Sommerfeld free electron model at T equal to 0 Kelvin. Below EFO are filled and all those above it are empty. Okay, so what does it mean? So okay, if we go to just the simple definition, okay, definition I will read out. So Fermi level means the highest value of energy. Energy means the band energy that electrons can have at a temperature of 0 Kelvin. Okay, or in other words, suppose you are maintain the temperature of your metal or semiconductor at 0 Kelvin. So at that particular temperature, what can be the highest value of energy that can be occupied by electrons? So that highest value of energy is the energy, or this energy level is called the Fermi level. And at T equal to 0 Kelvin, so you remember, okay, T equal to 0 Kelvin is the main identifying factor here. So at temperature T equal to 0 Kelvin, all energy levels above Fermi level are empty. Empty means Energy levels above Fermi level are not occupied by electrons, whereas below the Fermi level, all energy levels are full with electrons. Okay, so you have understood this much. So what is Fermi level? Okay, we'll read the definition. What is Fermi level? Fermi level is the maximum value of energy that electrons can occupy at a temperature of 0 Kelvin. Energy states above the Fermi level are empty at T equal to 0 Kelvin, and energy levels below the Fermi level are full. Below the energy levels below the Fermi level are full at T equal to 0 Kelvin.
So, sir,
Okay.
Fermi energy for a particular material is constant.
Yeah. Yes.
Okay.
So this they have like fixed values of Fermi levels. So yeah, but yeah, that's the thing. But where this Fermi level will be
change with temperature. It is change with temperature. Fermi level change with temperature or not?
No. If Fermi level, if you increase the temperature, then what happens? Some electrons will jump over the Fermi level and occupy some higher energy states. Okay, that thing will come to. Okay,
so
you see this figure
energy
now,
will increase.
this particular figure. If you see this figure, so okay, the first figure, it is for a semiconducting material. Okay, for intrinsic semiconductors, the Fermi level lies exactly between the valence band and the conduction band. Okay, you can see here. But here, in the first figure, it is the intrinsic semiconductor and maintained at a temperature of 0 Kelvin. But these two figures on the right side, so you have increased the temperature of the semiconducting material. These are semiconductor materials, and there is a gap between the valence band and the conduction band. You are increasing the temperature, and this curved thing you have seen, the brown curved thing, that is the Fermi function, Fe. What is Fermi function? We'll discuss in a while. So that Fermi function is still.
Sir, your voice is not coming, sir.
Internet. Okay, maybe it's some internet problem here.
Yes.
Now can you hear me?
Yes, sir.
Now?
Yes, sir.
Okay. So so Fermi level, the Fermi function Fe is the Fermi function. So Fermi function changes its shape when you apply a temperature above 0 Kelvin. Okay, that means changes. Why it changes? Because it's given in the caption here itself. Some electrons have energy above the Fermi level. That means at 0 Kelvin, no electron can be there at the conduction band. But if you are increasing temperature, then some electrons will overcome the Fermi level and they will move to the conduction band. And if that happens, then this Fermi function changes its shape. Okay. So this middle one, can I write something here? So, okay, let me try to write something. EF. EF is the Fermi level. Sorry. Yeah, Fermi level is written in language itself. So why am I writing again? Anyway, you can see the Fermi level is the middle one exactly. Okay. You can see in the figure, middle one means for an intrinsic semiconductor, Fermi level is above the Fermi level. So symmetric means, so you can see this is the middle point. Okay, maybe I have to draw a small straight line. Okay, I have drawn a small straight line. I can change its shape, form its shape if I do. To change its size. This blue line. So okay, so in some note I might have written this, but I have to find that note. But anyway, so if I can just tell you, so Fermi level is the middle one. Okay, this dotted line here in the second figure, and this brown line, this is for Fermi function Fe, and the Fermi function Fe is actually symmetric about the Fermi level. Okay. So here in this case, it is it has this particular shape, but if you keep on increasing the temperature, the Fermi function Fe will change its shape a little bit, but nevertheless it is always symmetric about the Fermi level. So this is the Fermi level. Okay. So this is the Fermi level. And why this happens? Because electrons jump from the valence, electrons above the Fermi level, and they can occupy some energy states at the conduction band. Okay, that's why the shape of this Fermi function, this brown curve, changes Fe, but nevertheless it is symmetric about the Fermi level. Okay. So anyway, I should read the notes, then it will be more clear to you. So, okay, I'll read the notes, Fermi level. So from Sommerfeld free electron theory of metals, the energy eigenvalues are Ek is equal to 1 by 2m h by 2l whole square n square. Okay. So that is the energy eigenvalue that electrons can have while occupying some energy states in valence band or conduction band. I mean, you know that electron energy values are quantized, right? Because electrons can't have all energy values, they will only occupy discrete or quantized energy values, and which you might have learned in quantum mechanics also. So in which semester you learned quantum mechanics? First semester, right? So in first semester, huh?
Yes, sir. First semester.
Yeah, first semester, and there you must have studied about like electrons in a potential well, etc.
Yes,
so electrons always occupy discrete energy values. Okay, that's why this quantity n square is coming. No, so there is one n square dependence. That means electron energy values will be
discrete.
quantized. Yeah, discrete. Yeah. Okay, so I read the next paragraph. So consider the building up of, okay, so one more thing. So these notes were given to you from this Srivastava textbook, okay. Srivastava book for solid state physics. So I have this book, I purchased the book, but it was there in your library, many copies, but I don't know if right now it is difficult to access library, but anyway, I have the soft copy. Okay, so consider the building up of free electron gas by filling electrons into a box one by one. Okay, then it is written that the first electron will take minimum kinetic energy. So kinetic energy is very low, which is 10 to the power minus 55 electron volt. That means this is the energy for the first electron to occupy some very lower energy level. Okay. The next electron will also be able to take the same minimum kinetic energy provided it aligns its spin anti-parallel to the first electron. Okay, so here is one important thing. So in one energy level, there can be two electrons. Okay, but with a condition. What is the condition? So have you studied about Pauli's exclusion principle in chemistry.
Yes,
Maybe
sir.
you learn it in
Yes.
chemistry, right? Or also maybe
Yes.
in atomic physics. So what was the definition? If I remember, no two electrons can have
Can have the all
same.
same quantum numbers.
Yeah,
Uh,
exactly. All same quantum numbers. Yeah, like these quantum numbers were ms, ml, then s. So this
and L.
spin, yeah, angular momentum spin, those different four quantum numbers. But there is a catch. What is the catch? That if one electron has spin up, okay, maybe I can draw briefly. This is the spin of one electron, as you can see. Then the other electron will have spin down. Okay. So this is one electron, but in the other case, the other electron will have spin down. If the electrons have spins like this, like two electrons, they can occupy the same energy level, provided one electron has spin up and the other electron have spin down. That means they should have anti-parallel spin. Okay. Anti-parallel means one is spin up and the first one is spin up, this one, and this one is spin down. Okay. Why this? This must happen because Pauli's exclusion principle must be satisfied. If both have spin up, then there will be repulsion and the electrons cannot exist in the same energy level. Okay. And then in the note it was written the third electron can take the minimum energy. Why the third electron? Because if we include a third electron, so that will have either spin up or that may have spin down. But we already have one spin up electron, therefore there cannot be any third electron. So I am deleting the third electron from the picture. Okay. The third electron cannot take this minimum energy. Okay, so if the third electron cannot have minimum energy, so this third electron will have to be added to the immediate higher energy level. Okay, so in one particular, suppose energy level 1 and energy level 1, there will be 2 electrons. In energy level 2, you have to add another 2 electrons. Why you cannot add 3 electrons in the same level? Because otherwise 2 electrons will have same values of quantum number, which is a violation of Pauli's exclusion principle. Okay. Some of you, if you don't remember Pauli's exclusion principle, you may just revise it. Maybe in Google you can type Pauli exclusion principle. Then you can recall what was that. Okay. So third electron will go to the next higher energy level. So then what was written, thus when added, this electron goes into next slightly higher energy level, slightly E0 plus delta. So E0 was the energy of the first energy level and delta is the slight difference between the first energy level and the second energy level. Then written, the fourth electron will take the energy again E0 plus delta. The another electron, fourth electron, will also be in the slightly higher energy level, but again with the same condition that this fourth electron must have spin anti-parallel to the third electron. Okay. So like this particular configuration of electrons have to be satisfied, one with spin up and the other one with spin down. In this way, addition of electrons will continue until all available electrons, suppose n number of electrons have been used. Suppose you have n number of electrons in a solid, n is like a very high number. So you can't imagine. So if you remember what in a semiconducting material, this concentration of electrons can be, I think, 10 to the if I am right, okay, because I'm not very sure right now. It can be 10 to the power 16 per centimeter cube, like that. Okay, you check it. Okay, I don't remember the exact value, but it is 10 to the power 16 or of that level or like that. Okay, I don't remember the exact value, but what I mean to say that it is a very high value. Okay, therefore, if this many electrons are there, so you can imagine how many energy levels will be required to accommodate all the electrons in those energy levels. Okay. Anyway, that's a different thing. I'm coming back to the notes. In this way, addition of electrons continues until all the available, say, n number of electrons have been used. Okay. Okay. For simplicity, it is taken that n is an even number. Capital N is even number. Why even number? Just for our simplicity, because then thus first n by 2 levels will be filled. Okay. Okay. So if you try to understand, in each energy level you can accommodate how many electrons? 2 electrons, and you have total n number of electrons, capital N number of electrons. Okay. You have capital N number of electrons. If you can see, I have written capital N. Okay. Capital N number of electrons are there, and we have maximum 2 electrons in a given energy level. Therefore, how many energy levels will be required? We will require capital N divided by 2 number of energy levels. Okay. Because each energy level has 2 number of electrons. Okay. That is what is written. The first n by 2 levels will be filled, and higher levels will be completely empty. Okay. So up to the n by 2 levels, n by 2 number of levels, electrons will be filled, and above this particular level there will be no energy level filled with electrons. Why? Because all the electrons have been accommodated in n by 2 number of energy levels. Okay, but this is true under one condition, and what is that particular condition? That particular condition is the temperature of the material should be 0 Kelvin. Okay, now I cannot change it. There's some problem with word. Okay. The temperature of the material is 0 Kelvin. And all these things that we have been discussing will hold good only when the material has a temperature at 0 Kelvin. Okay. Then the next line, what we have written, the n by 2 level in this case, that means the level which divides filled and empty levels on the highest filled level is known as Fermi level. Okay, the corresponding energy is called the Fermi level, Fermi energy. So, what was the definition of Fermi energy that we have discussed in the introduction? The highest energy level. The highest energy level occupied by electrons at absolute 0 Kelvin temperature, or absolute 0 temperature, or 0 Kelvin temperature. Highest value of energy. And what is that particular level of energy this time? N by 2. Capital N by 2 is the highest value of energy occupied by the electrons. And any energy level above N by 2 value will be vacant or empty, or any energy level below n by 2 value will be full. Okay, so you understood this. Above n by 2 energy levels will be empty or vacant, and below n by 2 energy levels will be completely full. But under what condition? Under the condition that the semiconducting material or the material has to be maintained at 0 Kelvin temperature. Okay, so that is the main condition. That is where the concept of Fermi energy or Fermi level comes. Okay, and therefore the n by 2 level, this particular level is known as the Fermi level. Okay, this particular level is known as the Fermi level. The corresponding energy, the energy corresponding to the Fermi level is known as the Fermi energy. Okay, so more or less you have understood this much. Okay, so then there is another topic, and maybe we can discuss this in the next class. What do you say? What's your opinion?
Yes, sir.
Okay, sir.
Okay, so I suggest you, there is one topic called concept of Fermi energy and Fermi level. You revise this, but I will discuss in the next class in 15-20 minutes. Okay. Then in the next class, I will see what we can discuss. Maybe we can discuss about magnetism, some topics on magnetism. Okay. So this topic, in your note, it was given to be concept of Fermi energy and Fermi level. And there we introduced the Fermi function Fe. So you also learn a little bit about Fe. Okay. So we will do it in the next class. But now you don't go. Let me take some screenshots again, 1 or 2 screenshots in 1 minute. Then we'll end the session. Okay. Okay, so I think we can hang up today, and I am stopping the sharing. And your next class, your next regular is Tuesday, right? So on Tuesday, I will schedule another class. We will discuss the remaining part of Fermi energy, Fermi level, and I will see some topic of magnetism we'll discuss. Okay,
Yes,
so thank you for joining today, and take care. Enjoy your weekend.